As we move towards the end of this section, we need to learn about the big difference between the way primitive types and objects are stored in memory. And this is actually a very practical aspect and one that causes a lot of confusion in beginners. So let's actually start by writing some code this time to understand what the confusion actually is, so that I can then show you how it all works behind the scenes. So right now, I'm not gonna explain how the code we will write now works, but I will just show you what the source of confusion is. But for now, let's start with a simple example with primitives. And so remember, primitives are like numbers, strings, booleans, etc. So simply setting the age to 30. And then I'm creating a old age variable. And this one I will set to the age, because now it is my birthday basically. And so my age changes to 31. But I still wanted to preserve my old age here in this variable. Okay, so let's log the results to the console now. And they should be pretty much what we expect at this point. So you see that my current age is 31 because, well, I changed the original one from 30 to 31. But the old age is still 30 here. And that's because I set it here at this point of the code to age, which was still 30 at this point. And so then changing the age here from 30 to 31 did of course not affect the old age variable. Again, because at this point here, age was still 30. All right. So here, hopefully there is not much confusion. Everything works just as expected. But now let's create another scenario which has an object. So I'm simply going to create an object for me with the name of Jonas and age 30. And now let's copy this object, because let's say that I have a friend who's also called Jonas. And so instead of creating a brand new object from scratch, I will just copy the me object. So const friend equals me. Okay? And so now both the name and the age are the same, but let's say that we have different ages. And so let's change the age of my friend. And that's pretty straightforward, right? So let's say that he is 27 years old. But of course, we did not change me.age, right? So let's now take a look at both of them in the console. So first my friend. So that's the friend object. And then also me. Or we could say Jonas, it doesn't really matter. But what matters is that we will see the me object. And what do we think will happen now? So let me show it to you. And now we get that both me and my friend have the age of 27. And that looks a little bit strange, because all we did was to change the age of the friend, right? Nowhere here I have me.age equals 27. But still, for myself, so here at the me object, the age is also 27. And so that is what I mean by source of confusion. And so in this video, let's now find out why it works this way. Now, before we can understand the code that we just wrote, we need to review some basics here. First, we need to remember about JavaScript's primitive data types, which are number, string, boolean, undefined, null, symbol, and big int. Then everything else are basically objects. So objects created with the object literal, arrays, and even functions are all objects. Now, when we're talking about memory and memory management, it's usual to call primitives primitive types and objects reference types, because of the different way in which they are stored in memory. Next, we need to remember about the JavaScript engine. So the engine has two components, the call stack where functions are executed and the heap where objects are stored in memory. And that's right, all our objects, or in other words, reference types, will get stored right in the memory heap. And I mentioned that when we first talked about the engine, but now you will finally learn how that actually works. On the other hand, primitives, or primitive types, are stored in the call stack. And with that, I mean that primitive types are stored in the execution contexts in which they are declared. But for the sake of simplicity, let's ignore that detail now and simply say that primitive types are stored in the call stack, because that's where execution contexts run. Alright, but now how does all that actually work? And why did our code example earlier behave in that weird way? Well, let's find out. So here we have the two code examples from earlier, as well as the engine with call stack and heap. And let's start by looking at the primitive values example. So when we declare a variable like age equals 30, what actually happens inside the JavaScript engine and the computer's memory? Well, first, JavaScript will create a so-called unique identifier with the variable name. Then a piece of memory will be allocated with a certain address, so 0001 in this example, and finally the value will be stored in memory at the specified address. So in this case, the value 30 will be specified at memory address 0001. And remember, this all happens in the call stack where primitive values are stored. Now, what's extremely important to understand here is that the identifier actually points to the address and not to the value itself. So we would say that the age variable is equal to 30, but in fact, age is equal to the memory address 0001, which holds the value of 30. All right? And this subtle distinction is very important to keep in mind. Now, in the next line, we declare old age to be equal to age. So, knowing that a variable actually holds a memory address, what should old age look like? Well, it will simply point to the same memory address as the age variable. And so, it will look like old age is simply 30 as well. Great, but now in the next line, we set age to 31. So what will happen then? The value at address 0001 will certainly not become 31, because that would change old age as well, since they both point to the same address. So that would make no sense at all. Also, the value at a certain memory address is immutable, or in other words, it cannot be changed. So instead, what's going to happen here is that a new piece of memory is allocated, so is created, and the age identifier now simply points to the new address, which is holding the new value of 31. Alright, and that's why when we lock both our variables to the console in the end, they both return exactly the values that we expect. Now with reference values, things work a bit differently, which is the reason why this example gave us that unexpected weird behavior earlier in practice. So what's the origin of this weird, unexpected result? Well, when a new object is created, such as this me object, it is stored in the heap. And such as before, there is a memory address and then the value itself. Now, in the case of reference values like this me object, the me identifier does actually not point directly to this newly created memory address in the heap. So in this example, D30F. Instead, it will point to a new piece of memory that's created in the stack. And this new piece of memory will then point to the object that's in the heap by using the memory address as its value. In other words, the piece of memory in the call stack has a reference to the piece of memory in the heap which holds our me object. Okay? And that's the reason why we call objects reference types in this context. So again, when we declare a variable as an object, an identifier is created which points to a piece of memory in the stack, which in turn points to a piece of memory in the heap. And that is where the object is actually stored. And it works this way because objects might be too large to be stored in the stack. Instead, they are stored in the heap, which is like an almost unlimited memory pool. And the stack just keeps a reference to where the object is actually stored in the heap so that it can find it whenever necessary. Now, moving on in the code, we create a new variable called friend that we set equal to the me object. So what will happen here? Well, just like with primitive values, the friend identifier will point to the exact same memory address as the me identifier. And again, that address contains the reference which then points to the object itself. And like this, the friend object is now essentially the exact same as the me object. Do you see that here in the diagram? So here comes the interesting part, because now we're actually going to change a property in the friend object by setting friend.age to 27. So what happens then is that the object is found in the heap and the 30 is changed to 27. Great. And by the way, even though we defined the friend variable as a constant, we can actually still manipulate the object without problems. And when we think about that, it makes sense, because we're actually not changing the value in memory for the friend identifier. It is still D305, so the reference to the object. All we did was to change the value in the heap, and that's not a problem. So it's a misconception that all variables declared with const are immutable. In fact, that is only true for primitive values, but not for reference values. So keep that in mind whenever you're working with const. Anyway, as we log the friend variable to the console, we get the age of 27, just as we said it before. But then, when we log the me object, we get that weird behavior that we could previously not explain and not understand. But with everything that we learned in this lecture, it actually now makes sense that in the me object, age is now also 27, even though we never changed me.age directly. And the reason for this, as we can see in this slide, is the fact that me and friend actually point to the exact same object in the memory heap. So whenever we change something in this object, it will always be reflected in friend and in me. So in both these objects. So these are basically just two different identifiers pointing to the exact same value. And once again, that value is the memory address D305, which points to the reference in the memory heap. And one important implication of this is that whenever you think that you're copying an object, you're really just creating a new variable that points to the exact same object. And this has huge implications for the way JavaScript works in practice, and we will see that in the next video and throughout the course. Now, there are actually ways around this, as we will also learn later, but in general, this is how reference values work in JavaScript. So make sure to really understand this, as well as the implications that this behavior has, even if that means that you have to rewatch this lecture, or at least the explanation of this slide. All right? Then, once you really understand what happened here in this example, let's understand primitive values and reference values even better in practice in the next lecture. But before we do that, let me just quickly take a second and mention 3 more really big topics about how JavaScript works behind the scenes that will not be in this section, but closer to where we actually need to learn about them. For example, one fundamental concept of JavaScript is prototypal inheritance, but we will only talk about that in the object-oriented programming section of this course, because it doesn't make sense to learn about this now, only to then forget it all until we finally reach that section. The same is true for a detailed lecture on the event loop. So I already introduced the event loop in this section, but in the section about asynchronous JavaScript, we will dive really deep into how exactly the event loop works and why it's such a fundamental piece of the JavaScript engine. Finally, we will have lectures on how the DOM actually works behind the scenes too. And that's going to be in the advanced DOM and events section, so that you can then apply what you learned there right away. Okay? And with that being said, let's now move on.